Lecture 1.14, and this is going to be on thermal diagrams and equations, the advanced problems that some people have been having trouble with. And it appears to me that a lot of people picked a lot of things up Friday regarding how to start these types of problems. But what I have here is a practice problem I've just wrote up, and I have it available on the website. So if you want to download it or look at it, write it down, and do it, or try to do it first, and then look at my tutorial here, you may do so, or just follow along, whatever you can to figure out these things. It's modeled in the way of the quiz. Okay, it's not the same problem, but maybe you can find some hints built into this tutorial. Okay, bottom line is learning in any way you can. Okay, so this practice problem starts with a styrofoam cup that is a certain amount of grams of water at a certain temperature, okay, with water in it. They're going to be thermally equal at equilibrium. So let's draw ourselves the cup, and let's make it thicker so I can see what's going on here. And the cup, of course, is the calorimeter. And now I'm going to add some water. All right, so I guess I'll have to make it blue. And then we're going to add a cup. We have an ice cube. Let's have the ice cube here. All right, it's floating, less dense than water. And then we're going to have our copper block. Let's make that green. Okay, and then we're going to have our temperatures. And we have, what, 58.0 or 58 degrees Celsius for the water. The block is 10.3. And of course, the cup is 58 degrees Celsius as well. And we're going to show the flow of heat from the high to low, or the rugby players to the geeks in the park. And we're going to flow this way. So energy is flowing, obviously the hot water to the cold block, and also the cup to the water. And we're also going to have the ice cube, which is endothermic, absorbing energy from the water. So from this flow energy diagram, you should be able to figure out what's going on and who are the players, assuming this entire system is closed. Big assumption, but we'll have to do that. So what we're going to say is the energy that is being released is equal to the energy that's absorbed. Okay? Now, given this statement, which is basically the first law of thermodynamics, that all energy is conserved in our closed system, who are the players? Who's releasing energy? Well, we know the water, Q of the water. We see the water is giving its energy to the block. Okay, also the cup, which is in thermal equilibrium with the water. You can always assume that unless I tell you otherwise. Who's absorbing? Well, obviously the block is, so we have Q of the block. And don't forget our ice cube is endothermic. So you have Q of the ice cube. Now let's stop here with the ice cube for a second. How do I know it's endothermic? Well, if you didn't know that a solid going to a liquid is climbing an energy ladder, I also kind of gave you the hint here, is that that's the energy it took for this solid to go to a liquid, and energy in the reactant side means that it's collectively an endothermic process. It needs energy. So that's a hint there. But I'm also giving the entire energy it takes in this reaction. So that Q of the ice does not have to be calculated for. It's given to you as that value. So that's something to think about. Okay, so let's go on to the problem, and let's write out our equations based on our thermal diagram. Now, I think most of you at this point probably see what's going on. Okay, but I don't know why I'm stuck on this now. Okay, but let's throw something else for a second. We have this diagram, and we know that the water and the cup collectively are warmer. They're going to get colder. And we know that the block and the ice are going to get warmer. So the temperature finals, okay, temperature final is going to be lower for that of the water in the cup and higher for the block on the ice. Now the block, I put the ice here, but truthfully, we're not going to consider the block of ice in our thermal diagram because we already have that total energy given to me by the reaction. Okay, that's one little key point here. Okay, so now we're going to go on to the problem. I don't know why that just happened, and that really stinks. Get back to where I was. Okay, now we're there. Now we have some room. Okay, so let's scroll down here and start writing our problem out. So we've got Q of the water, so that's the mass of the water, MC change in T. That's the formula that we've been using for our Qs. Okay, plus MC change in T for the cup equals MC change in T for the block. And of course, we're adding this value. So let's go to some different colors. Let's go black. Okay. So Q of the water. Okay, the water is 335 grams, and our specific heat is 4.18 joules per gram per degree Celsius. And we have 58 degrees as my initial temperature. All right, and the question is, where does it go? You know that I'm trying to constantly keep these things positive because these thermal equations are positive. So the question is, where do I do with that number? Well, the question is, the answer here is in this diagram. We know the final temperature is going to be lower. So the initial temperature is higher. So what we're going to do here for these guys, to keep this positive, we're going to go initial temperature minus final temperature. So the initial temperature is 58.0 degrees Celsius, and we're going to minus by temperature initial, temperature final, sorry. Okay, since the whole idea or the problem is to find the final temperature that all these things are equal. So I'm keeping it positive, and this diagram may help you. Okay, the water is going down in temperature, the initial, so I'm going Ti minus Tf in this case because Tf is smaller to keep everything positive. Okay, now I'm going to add, okay, Q of the cup, and the cup is 100.35 grams, and the specific heat converted is 1.30 joules per gram per degree Celsius. Remember, you got to convert that. I've shown you how to do that in other tutorials. And same idea here, it's going to be 58 minus TF, okay, and that's equal to the Q of the block. Okay, so Q of the block is mass of the block, which I get to be 35.5 grams. Specific heat converted is 0.385. I'll leave out the units because I'm running out of space. And then this side, we know that the final temperature is going to be higher, so it's going to be TF minus. All right, so TF minus that initial temperature, which is 10.3, and again, I'm keeping everything positive. Okay, 10.3 degrees Celsius. Sorry, I didn't really space out this very well. Okay, now I left something else out, and I'm going to rewrite this in a second. Let me rewrite this bottom number for you. Okay, so I just rewrote what I just did here. Here's the Q of the water, Q of the cup, Q of the block. Notice it's TF minus 10.3 or its initial temperature. Notice 10.3 is lower, temperature final is going to be higher, so I'm keeping everything positive and using negatives here. And notice I used the heat already given to me by the ice right in here. And that's what I'm doing at this point. That's everything set up. Okay, so look at that carefully. You notice it's the energy that's being released on this side equals energy absorbed, including the ice cube, and I'm using the energy given to me as its Q already. So if that was hanging you up, now you've got that down. Now it's just simplifying. Okay, so instead of watching me simplify, I'm going to kind of do this in steps. I'll be right back. Okay, so um, these values here, remember we're distributing these two numbers multiplied by that. That gives me this number. And I'm taking those same numbers, 35 point times not this, but times TF. Okay, so that's this number. Then of course this number times this number times this number gives me this number. And probably a better way to do that is this. Next time is this number times this number times this gives me this negative. So notice the negatives are arriving because it's minus TF. Okay, and of course this number times this TF is this TF, and then of course next is this number times 10 to the 3 is here, and don't forget this value was carried originally from the equation in the formula. Okay, and let me continue simplifying for you. Okay, so there it is. I have simplified for you some more. Okay, clearly I've added, in this case, I was taking the non-TF numbers and combining them. And that's what got me this number. And I took the TF numbers and I combined them to get this number. And here there was only, oh, I got my TF right there. Ooh, okay. Okay, I have the TF right there. And of course I combined these numbers to get that number there. Notice the positive went away because this number is so much bigger than this negative when I add them together. Okay, let's continue finally doing some more simplification. Okay, then I have simplified some more by just doing some simple algebra. This was a negative 1530.755, and I added the same value to get rid of it. Have to put it on a different side of the equation. What you do to one side of the equation, do to another. That gives me this value. Then I subtracted the 997.24 from this side, and I did it to this side. This cancels it off, and this I'm adding that negative value, but it's much smaller than this value, so it came down a little bit. So I'm left with these two values, and I divide by the 1544. Okay, and I get temperature final to be, let me put that in my calculator. I didn't do that. So 78804.566 divided by 1544.4225, and I get my final temperature to be 51.025. I believe we're going to round to 3 sig figs. The least significant number is 3. Yep. So I round to 3 sig figs. So 51.0 degrees Celsius. That's my final temperature final for everything. Now that doesn't include the ice because the ice is not water. But the point being is now I have final temperatures. So that final temperature is 51. We started at 58 for the water, and we started at 10.3 for the block. And it kind of makes sense, and you've got to make sure your numbers make sense, especially if you do all this work to see if it makes sense. Our water didn't go down that much, okay, but the block did change a lot. And now why? Of course, specific heat differences. Now this isn't as drastic as your other problems, and here's the reasoning behind that. You had the ice taking energy away from the water to drop it in even lower amount. So if it wasn't for this ice to take energy from the water here, okay, this temperature change would be very, very insignificant. Okay, in fact, I believe I did the problem out without the ice cube, and I actually got 57.5 or 6 or something like that, almost 58. So it really, it was the water, the ice, that really tipped the scales to make this go a little bit lower than it normally goes, and that should make some sense to you. So I hope that helped. Okay, the whole process, the whole idea behind these very complex thermal problems, you're not going to find that complex anymore. Draw yourself a diagram. Figure out who's releasing energy, who's absorbing. See what team they're on. There are cues for all the individual components. Sometimes I may give you an equation, Okay, if you notice, I'm always giving you different spins on these problems, and then you just plug them in and keep track of your negatives and positives in terms of temperature final, temperature initial, because we want to keep that positive. We're not adding that negative in. So I hope that helped, and good night.